vertical circles. Tom, this is a bit strange. I used to do horizontal circles first because they're easier, and then I would do vertical circles as my lesson 3. But my students told me actually the tougher questions, because there was more in them, made it easier to spot the patterns and kind of come up with the setup and how to do this. So I'm doing vertical circles first, which means our circles are going to be vertical. What's our key idea? If you're moving in a circle, which way are you accelerating? Toward the center, inwards. I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Which way is the winning arrow going to be pointing if we're moving in a circle? Okay. You may want your formula sheet out because we're going to be using the v squared over r and the 4 pi squared r over t squared, unless you have those memorized. A person rides in a Ferris wheel. I need to pause for a second. How many of you have been on a Ferris wheel before? Okay. Is that considered a thrill ride or a tame ride? Tame-ish. Okay. A person rides on a Ferris wheel, and let's have them sit on a Newton scale that measures normal force in newtons. At the bottom of the Ferris wheel, what does the scale read? Does the normal force equal mg? Is the normal force bigger than mg? Or is the normal force less than mg? And convince me. You know what? This is a job for a free body diagram. You're going to be doing a lot of free body diagrams again in this unit. So here's the person. What are the forces acting on this person? Get the obvious one. Which way? Down. What else? Which way? Pause. 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 What path is this person tracing out? A circle. Which way must my winning larger force be pointing? Toward the? So am I going to draw normal force bigger or smaller than mg? Has to be. So what's the correct answer? A or B or C? And from my explanation, free body diagram right there. What that means is, because remember, what you think of as your weight is actually the normal force. You feel heavier at the bottom of the Ferris wheel. I wonder if you feel lighter at the top. On a Ferris wheel, people feel light at the top and heavy at the bottom. Why does this happen? So Thomas has already convinced us why we feel heavier. You're moving in a circle, which means you are accelerating towards the center, which means your net force must be pointing towards the center. Let's look at the top. This is a job for a... What are the forces acting on the top? Get the obvious one. Which way is mg pointing? Towards the center. And so I'm going to draw normal force, but since we're moving in a circle, I know that the winning force has to be pointing towards the center, which means mg is going to be bigger than normal force, so your normal is going to be lighter. At the top, normal force is smaller than mg. In Latin, the word centripetal means toward the center. And so we say when you're moving in a circle, you are experiencing a centripetal force and a centripetal acceleration. I'm going to use the letter C as my abbreviation as a subscript. But you know what? If you don't want to remember the word centripetal, conveniently the word circle also starts with a C, and most of the kids, when they see FC or AC, they just think, oh, circle. But I'll use the centripetal term because I'm a physics nerd. So by Newton's second law, there must be an unbalanced force in the same direction as the acceleration. An object moving in a circle has a centripetal net force. Here is by far the most common mistake kids make. Okay, so some like to use the following notation: AC for centripetal or inwards acceleration, FC for inwards or centripetal net force, where the C means centripetal. Kids do this, okay. F equals what? Okay, so I see kids do this all the time, and then they go like this. What did they forget to write? No. See, it's so Captain Obvious, you'll miss it. What? Because the acceleration equations are so complicated, they forget to tuck the m in front. It's by far the most common with this one. They'll go, oh, it's 4 pi squared r over t squared. No, you just told me that F equals A. Ma? Yes. So don't make that sloppy mistake. Okay? So handy note. In our winner minus loser approach, the centripetal force will always be the net force. What that also means is FC never shows up on our free body diagram. You'll notice nowhere here do you see FC. The same way, Thomas, when we did winner minus loser equals Fnet never showed up on the free body diagram. Everything that showed up was in the winner minus loser portion of the equation. So you're never going to put FC on your free body diagram. I'll dock marks if you do that. In the previous example, the Ferris wheel is a rigid wheel. The top and the bottom of the wheel will always have the same speed. And that's uniform circular motion, constant speed. This is not always true. There's something called a pendulum, a vertical pendulum. If I spin this vertically, do you notice if you watch really close from the side, it slows down at the top and speeds up at the bottom? This is a much more difficult situation to analyze. In fact, we can only analyze a pendulum spinning on the end of a string when it's at the very top and when it's at the very bottom. We can't analyze those, but if it's here or here or here, the physics gets yucky. We need vectors and calculus, and actually polar coordinates would work best. A whole different way of thinking about graphs. So example 3 says, write force equations for the vertical pendulum at the top and at the bottom. Let's do the bottom first. What are the forces acting at the bottom? Get the obvious one. mg down. What path is this pendulum tracing out? A circle. So where is the winning net force pointing? Toward the... What force is that? String. So, yes. Now, this is a problem because here I'm using capital T for tension, and here capital T is period. Sorry, don't get them mixed up. Who's winning? Who's losing? At the bottom, your equation looks like this. Tension minus mg equals mac. And AC can either be v squared over r. Now, because you're going faster at the bottom, you would go mv2 squared over r. You would use the bottom speed there. What about at the top? This is a job for a free body diagram. What are the forces acting at the top? Get the obvious one. Oh, sorry. What? mg. What else? Tension. Which way? Oh, okay. I got two forces pointing inwards. Who's winning? It's a bit of a trick question. They... No, don't cancel. Who's winning? They both are. Who's losing? No loser. So at the top, my equation looks like this. Tension plus mg equals mac. Tension plus mg equals m v1 at the top squared over r. So in a vertical circle, there can be tangent forces that speed up the object and slow it down, especially if there's a string. Now, if the circle is rigid like a Ferris wheel, then Nina, we know the speed is constant. The v that we have will be the v we can use anywhere. The net inwards force is still mv squared over r, or it could be m4 pi squared r over t squared, where that capital T is the time to go around once, the period, not tension. And there are no horizontal forces. So there's kind of a front view, there's kind of a side view. Let's do some crunching here. I like example 4, I like example 4, I like example 4. Is this a Ferris wheel? Sorry? How do you know this is not a Ferris wheel? Well, it says roller coaster. Yeah, but looking at the picture, how do you know it's not a Ferris wheel? Because on a Ferris wheel at the top, which way is your head pointing? So we have to be careful. The normal force points in the same direction as my head. In this situation, the normal force at the top is pointing down. where in the Ferris wheel, the normal force at the top was pointing up. So be careful with your free body diagrams. A 70-kilogram passenger is moving at 10 meters per second at the top of an upside-down roller coaster. Find the force that the seat exerts on the person. What's this question really asking me to find? Sorry? The normal force. This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. What else? Who's winning? Are we moving in a circle? AC. Now, there are two equations for circular acceleration. Circular acceleration is v squared over r, and circular acceleration is 4 pi squared r over t squared. Which one am I going to use? Jacqueline, how do you know? They gave you the speed. I got to be fussy. Speed. Okay. By the way, the one you'll use the most at Playland is this one, because getting the speed of the loop, I do have one radar gun and one group can borrow it, but to get the speed of a coaster as it goes by you is very difficult. But to time it, that's easy. So we'll almost always be using the period one. But for now, yeah, so we have this. Normal force plus mg equals mv squared over r. What's this question asking me to find? How do I get the normal force by itself? Okay. Oh, subtract, Mr. Dueck. Sheesh. So we're going to get the normal force equals 70, 10 squared, r, oh, they gave me r in the picture, over 8, minus 70 times 9.8. What do you get? Sorry? 189? Yeah. Rounded off properly? What's this person's normal? 70 times 9.8. Can you know what? That's roughly 700 newtons. Yes? So this person feel heavier or lighter? Yeah, this person would feel like they were about to fall out of the coaster because most of you are not used to feeling a lighter normal force. They're not going to fall out of the coaster. They still got 189 newtons to play with. But you would shriek at the top of this. This would be a good thrill ride. You would give a good scream. In the previous example, what would happen to the normal force if the roller coaster moved slower and then faster? You know what? Okay. What happens if the coaster slows down? What happens to the normal force? Well, here's the speed in this right there. As this number gets smaller, what happens to this answer? Smaller. In fact, the slower it goes, the more you'll feel like you'll fall. Okay? So as a proof, let's do a lovely algebraic proof. We have this equation. Fn equals mv squared over r minus mg. As v decreases, Fn decreases. What about if we go faster? As v gets bigger, what happens to the normal force? Increases? So let's do the same proof. Fn equals mv squared over r minus mg. As v increases, Fn increases. Could you go so fast that you felt a bigger than normal? Could you go so fast so that the normal force was larger than mg? Yeah. I'd have to play around with the numbers a little bit, but I could have a high enough speed that we got an answer bigger than whatever 70 times 9.8 is. And then you wouldn't feel like you were about to fall out of the seat. You would feel like you were getting pressed into the seat. How many of you have been on California Screaming at Disneyland? It's now called the Incredicoaster. Okay? That loop there, at the top, you still feel like you're getting pushed into the seat. Okay, so that one there, you're going fast enough so that at the top you still feel heavier. That's done on purpose because Disney doesn't do scary thrill rides, they do entertaining rides. We're all used to feeling a bigger normal force. We're not used to feeling a smaller normal force. A smaller normal force, that roller coaster would be scary rather than thrilling, if you understand the slight difference there. Okay. Example 6. If the pendulum of example 3 or the upside-down roller coaster of example 5 were moving at the minimum safe speed, what would that imply about the forces? If they were moving at the minimum safe speed, what would that imply about the forces? Well, let's look at situation A, the rope. Watch closely, and I'm going to slow down. So right now I'm going really fast. I'm going to slow down to minimum safe speed. Watch the rope. Did you notice what happens for a split second in the rope there? If I'm right on minimum safe speed, how big is tension exactly? Exactly 0. Here, that's a problem probably because there it started to fall. But if I hit the magic sweet spot, the rope wouldn't be slack, but it wouldn't feel any tension. So minimum safe speed for spinning an object on the end of a rope, tension is 0. So we get this. mg, because tension is 0, equals mv squared over r. Let's get the v by itself. Oh, a mass cancels, yes? Let's get the v by itself. What would I do with the r? Times it over, and then how do I get rid of a squared? So we get v equals the square root of grr. What about in the roller coaster? Now, if in the roller coaster I went minimum safe speed so that you just felt like you were about to fall out, what would the normal force be? Exactly 0. Tension would be 0 for minimum safe speed with a rope. For a roller coaster, normal force would be 0 for minimum safe speed with a roller coaster. And so we get mg equals mv squared. Oh, you know what? We get the same expression, Mr. Dueck. The minimum safe speed for a roller coaster is the square root of grr. I guarantee you ride engineers know that one, right? And you would build a huge safety margin in. This is going to start to allow us to design roller coaster loops and ask, for example, if you give me the radius of the loop, how high does the hill that the roller coaster comes down have to be to make it safely through the loop? Otherwise, we're out of luck. In other words, how much potential energy do I need to turn into kinetic energy to make it through the loop? We'll talk about that in a few days, but we'll do some good roller coaster physics. How many of you have ever taken a bucket of water and stood and spun it in a circle like this and noticed that the water doesn't fall? You've tried that? Anybody else? A few more of you? Okay, and here's my next question, because I'm guessing this is also some of you. How many of you have then, on a nice hot summer day, done that and tried to push the envelope? How slow can you go before the water falls out? Right? Because if you get wet, yeah, great fun. But if not, it's kind of neat. The water is somehow defying gravity, or is it? So if we spin a bucket of water fast enough, it's possible to momentarily invert the bucket and yet not have any water fall out. Why? You know what this is a job for? Free body diagram, you say. What are the forces acting on this water? Get the obvious one. What else? Come on, what else? There is a normal force. The bucket is pushing on it. What path is this water tracing out? Who's winning? Toward the center. So an equation I have is this. I have normal force plus mg equals MAC. Normal force plus mg equals mv squared over r. Let's get the normal force by itself. Normal force equals mv squared over r minus mg. When will the water fall out? If the normal force is equal to what? 0 or less than 0, which doesn't quite make sense. But here's what I'm going to argue. I think we can say this. As long as mv squared over r is bigger than mg, as long as this number is bigger than mg, we'll have a normal force and we'll stay dry. We stay dry. Now, what's the variable that you can control? Can you control the mass of the water when you're spinning it? No. Can you control the radius of your arm? No. Oh, you can control the speed. And so this is what you did as a kid when you were slowing down. What you were really doing was solving this equation physically. How slow can I go before I get wet? How many of you actually tried that? Yeah? A few of you? Okay. It's a classic childhood, often at the beach with a little sand pail, right? The ones that all look the same. I like example 8. I like example 8. Example 8 is a cool question. I don't know if you've ever gone on a bump and gone over a bump really fast in a car and got that stomachy feeling. Here's why. A student is in a car traveling at 28 meters per second on a hill of radius 120 meters. When the car is at the top of the hill, what upward force does the seat exert on the student? Any thoughts on how I might want to solve this? A free body diagram, you say. What are the forces acting on the student? Get the obvious one. Gravity. Which way? What else? Am I going to draw a normal force bigger, smaller, or the same size as mg? Why must it be smaller? What path is this car tracing out? A circle. Where must the winning force be pointing? Toward the center. Are you seeing why my big rants last class? Hopefully they're tying into what we did today. So I can go like this. Nina, then, what's my equation? Who's winning? Who's losing? What does that equal? MAC. Which A am I going to use? Did they give me a speed or did they give me the period? Okay, so I'm going to go mg minus fn equals mv squared over r. Nina, what's this question want me to find? The upward force. What does this question really want me to find? How do I get the fn by itself? Oh, swappy dance, right? We can plus this to there and minus this to there. A little bit different from the other equation that we had, but close. So we'll end up with the normal force equaling mg minus mv squared over r. It's going to end up being m, 72, times 9.8, minus 72 times 28, don't forget the squared, over, what was the radius? 120. What's the normal force equal to? 235 newtons, is that correct? Yeah? What's the person's normal? 72 times 9.8. Can you crunch that really quickly? So at the top of the hill, do you feel lighter or heavier? That's the stomach feeling. How fast would we have to go in order for you to feel completely weightless? If you feel completely weightless, what's the normal force equal to? So for weightless, Normal force equals 0. That's not 0 factorial. That's just 0 exclamation point, aha. So I'll erase that because 0 factorial is 1. So you know what? We can start right here. Same equation. mg minus normal force equals mv squared over r. Except normal force is 0. Now, in the previous question, the masses didn't cancel. In fact, you'll notice when we analyzed this roller coaster back here, did the m cancel? In terms of what you experience on the roller coaster, the heavier you are, the more intense a roller coaster is. This is why little kids can go on amusement park rides. This is why, as you get older, you may suddenly find you can no longer stomach amusement park rides the way you could when you were younger. Okay? But you'll notice here, I think now, m does cancel. And I get this. G equals v squared over r. Let's get the v by itself. Oh, hey! Do I get v equals the square root of grr again? So, how fast? I kind of want to know. 9.8 times 120 square root. What do you get? Sorry? 34.3? Do me a favor, multiply that by 3.6. How many kilometers per hour is that? Sorry? So doable. Okay. What if you went faster than that? What if you went 40 meters per second? What would happen? If you're wearing a seatbelt, I don't think you would fly out of your seat. The car would leave the ground. Because the normal force on the car in B is 0, which, by the way, means if the normal force is 0, what's the force of friction between the tires and the car right then? Friction is what times what? Mu times the. So how much friction, how much steering do you have at that speed of 34.3? Pretty much none. This is also why if you're going over a hill really fast, you're in much more danger of losing control of your car than if you're going in a hill that's curving up. Okay? But yeah, if you went faster than that, because in B, the car has no normal force either. It's weightless as far as it's concerned. If you go faster than that, it's going to get air. And so now we're starting to look at some of the physics of stunt driving and things like that. Raj has a mass of 72 kilograms. He is riding a Ferris wheel of radius 12 meters, and he's moving with a constant speed. Oh yeah, because a Ferris wheel is rigid. You're always going to be moving at a constant speed. At the top of the Ferris wheel, the bench that he is sitting on applies a normal force of 450 newtons. Michael, what's A want me to find? You know what this is a job for, Michael? Wow, way to come up with a punchline there. Drop the mic and walk off, please. Okay. At the top or at the bottom? What's this question say? Because it's going to make a difference. What are the forces acting at the top? Get the obvious one. Which way? What else? Bigger, smaller, or the same size as mg? How do you know? What path is this person tracing out? A circle. Where must my winning net force be pointing? Toward the center. So, Michael, what's my equation for part A going to be? I'm going to be bold and go v squared over r right away. Since they asked me to find a speed, I got to get a speed in here somehow. Well, there it is. Okay. I guess we're going to get the... This is right around where getting the v by itself is a pain. First of all, to get the v by itself, I would times everything by r. I would divide everything by m. M doesn't cancel because there isn't an m in normal force and square root. I think what I'm going to do instead, James, I'm going to get the left-hand side as an answer. I'm going to plug in numbers on the left-hand side right now. What's the mass, Michael?
72.
I'm going to go 72 times 9.8 minus, what's the normal force? Now, instead of giving you the normal force in newtons, I could also have him sitting on a scale and tell you what the scale said in kilograms. How do I change kilograms into newtons? Multiply by? Okay, so that would be another just little, if I needed to create an extra mark out of nothing, if this was a written question, that might be what I would do, but they gave it to me in newtons. That equals mv squared over r. Let's crunch this left-hand side. I get 255.6. Yes, double check me. Equals mv squared over r. Now I'll get the v by itself. To do it before then, you can. It's just you got so many brackets and garbage kicking around. That's where it becomes less clear and more confusing. So there comes a point when I just say, forget it. So it's going to be r times 256.6 divided by m equals v squared. Oh, how to get rid of a squared? Square root. The speed that this Ferris wheel is going at. By the way, that means technically if you go to Playland and you bring a bathroom scale with you and you sit on it, and while you're on the ride, you quickly glance down at the scale, you could calculate your speed from that. Now, they won't let you bring a scale onto Playland, but you gotta, I wonder if your smartphone, if you sat on your smartphone, some smartphones do have a scale sensor, some of the Android ones. That'd be interesting. Nina's both laughing and also intrigued. Yes. What was the mass of this person? 72? 12 times answer button divided by 72 square root. You get 6.5 meters per second? 6.53 meters per second? How many of you have ever been on a swing at the playground and tried to see if you could go high enough to loop it? Come on. How many of you tried that when you were 6 or 7? It entered your mind. Oh, the dream. Can I go so fast? Can I put enough energy in that I can do a full looping the chains? Sadly, you can't. Well, you sort of can. It depends. Put your pencil down, look up. So, no. What's your homework? Number 1 is good. Number 2 is good. Number 4 is good. What happened to number 3? I don't know. 5 is good. 6 is good. 7 is good. So far I've assigned all of them my no. Skip 8. 12 is good. Now in number 12, I gave you the frequency. If the frequency is 0.8, what's the period? It's 1 divided by 0.8, whatever the heck that is on your calculator. And so for this one, you're going to use the 4 pi squared r over the period squared equation, not the other one. So 12 is good. And you can work on some of you still, many of you still owe me homework from last day too. Okay.